Hello everyone, welcome to the second lecture where we are looking at the previous year IITJEE Advanced questions on complex numbers. We have been looking at last 5 years problems. We have already seen problems from JEE Advanced 2021 and 2020. So now let's take a step back and now we move on to the JEE Advanced problems from the year 2019. So let's see. So this problem appeared in JEE Advanced 2019 paper 1. So let's see what it is. So what it says over here is that we have a set S, right? So this set S is the set of those complex numbers such that mod of z minus 2 plus iota is greater than or equal to root 5. So one thing is that when you read this problem, you can immediately recognize that this problem has a geometric interpretation because I can read it as z minus 2 minus iota, this distance is greater than or equal to root 5. So you can see the set of points whose distance is larger than a fixed radius and it will represent the exterior of a circle. So I'll just show it geometrically. The complex number z0 is the one which maximizes the value of 1 over mod z minus 1. So 1 over mod z0 minus 1 is the maximum of the set 1 over mod z minus 1. Then what is the principal argument of 4 minus z0 conjugate over z0 minus z0 conjugate plus 2 iota. Okay, so let's first try to understand what the set is. So the set S is the set of those complex numbers such that mod of z minus 2 minus iota is greater than or equal to root 5. So z minus 2 minus iota represents the distance of this point z from the point 2 minus iota. So here we have real axis and we have imaginary axis, and here is where the point 2 minus iota lies. So there is going to be a set of points whose distance with respect to z2 minus iota is larger than root 5. So basically if the distance equals root 5, then we get a boundary of a circle. But if it is larger than root 5, then it will represent the points which are exterior to a circle. So here we can check that actually origin also lies on the circular boundary because distance between origin and 2 comma minus 1 is exactly root 5. So here we now have something like a circle and this origin actually lies on the circle. The radius of the circle is root 5 and the points which are at a distance root 5 away from it are the points which are exterior to the circle, and circle is also included, right, because you have greater than or equal to root 5. So circle and the points exterior to the circle, these points are the ones which belong to the set S. Okay. Now we have to find that z0 which maximizes the value of 1 over mod z0 minus 1. So here basically we need to maximize 1 over mod z minus 1 such that z belongs to the above set S. Okay. Now if you want to maximize 1 over x, it's equivalent to minimizing x, right? So basically modulus is actually a positive number. So lower the value of mod z minus 1 is, lower positive value it is, the larger is 1 over mod z minus 1. So that's what is happening here. And so we have to find that z0 who is now such that mod z minus 1 is minimized. Now again this has a geometric interpretation because I can take this point which represents the complex number 1. So this is 1 comma 0 on 2D plane, and I now need to find a point on the set such that its distance from 1 comma 0 is the smallest. So first of all you can actually see is that the point whose distance is smallest from 1 comma 0 is going to be the one which actually lies on the circle rather than outside the circle. The reason is as follows, that suppose if there is some point which lies outside the circle and if I connect it with this point 1 comma 0, then it will intersect the circle at some point, and this point of intersection will have a smaller distance to 1 comma 0, right, because it directly lies on the line and in between the 2 points. So that distance is going to be lesser. So basically if I have some point q which lies outside, I can join q to 1 comma 0 and I'll get some point p on the boundary. Now distance between p and 1 comma 0 is lesser than distance between q and 1 comma 0. So it has to be lying on the circle. Now which is the point on the circle which minimizes this distance? So just think for a moment yourself and see whether you can figure it out geometrically. You can maybe pause the video and maybe discuss it in comments also. Okay, so I hope you would have figured out that this point is the one which actually, suppose if I join this point 1 comma 0 to 2 minus iota, then the point at which it intersects the circle is going to be the one which minimizes the distance. Why is it so? Because if I join the point 1 comma 0 to 2 minus iota, let's say this distance is d, then the distance between the point on the boundary which directly is obtained by connecting it to the line through 2 minus iota and 1. So this point, suppose if it is p, then this distance is going to be r minus t, where r is the radius of the circle, which is root 5. Now for any other point on the circle, right, for any other point on the circle, what we are going to have is that, suppose if there is some other point p prime on the circle, and let's say I have this point which is 1 comma 0, and I have this point which is 2 minus iota, then basically since it lies on the circle, this distance is going to be root 5, which is my radius, and let's say that distance between 1 comma 0 and 2 minus iota is d. Then by triangular inequality we have that this the line joining p prime to 1 comma 0, this distance must be greater than equal to r minus d, right? And at p, the value of r minus d is exactly achieved. So basically, to minimize the distance, what I can do is that I can draw a line from 2 minus iota to 1 comma 0. The point at which it intersects the circle is the one which minimizes the value of mod z minus 1. Okay. And how do I now find the point at which it intersects the circle? So basically the thing is that, so this distance, okay, so basically the idea is this, that so basically the idea is this, that we can actually find the phase and the distance of the point with respect to 2 minus iota. So first of all, any point on the circle can be represented as 2 minus iota plus root 5 times e to the power iota theta, okay, where theta is the relative angle of the line joining 2 minus iota to p. Now the line joining 2 minus iota to p actually passes through 1 comma 0, and we can check that the angle which this line makes with x-axis, we can actually find out that angle. So suppose if I have this point 2 minus iota and I have this point 1 comma 0, so basically what we can check is that we can actually find this sort of angle, and you can see that this is going to be, this height is 1 and this distance is also 1, so this theta is going to be pi over 4 over here. So let me call it theta prime, and the value of theta which it makes with positive x-axis is going to be thrice pi by 4. So here essentially with respect to 2 minus iota, the value is going to be, the distance of this point is going to be root 5, and the angle which this line makes is going to be precisely 3 pi by 4. So overall this point can be represented as 2 minus iota plus root 5 times e to the power iota 3 pi over 4, right? And now I can actually compute this value. So this is going to be nothing but cosine 3 pi by 4 plus iota sine 3 pi by 4. And so cosine 3 pi by 4 is going to be minus 1 over root 2 plus iota times sine 3 pi by 4, which is going to be plus 1 over root 2. And this point is then going to be 2 minus square root of 5 by 2 plus iota times minus 1 plus square root of 5 by 2. And this is going to be my point z0. Okay, so let's understand what we did over here again. So what we did was that if we look at the point relative to 2 minus iota, we know that it's root 5 distance away and it makes an angle of 3 pi by 4 with positive x-axis. So with respect to 2 minus iota, the point P is of the form root 5 times e to the power iota 3 pi by 4. And if I add 2 minus iota to it, I'll get the absolute coordinates. And we see that those coordinates, I have obtained them as follows. Now let's look at the expression which we want to find. So we want to find the principal argument of 4 minus z0 bar over z0 minus z0 bar plus 2 iota. So let's see what it is. So this is 4 minus z0 bar over 2 iota plus z0 minus z0 bar. Okay, so this is going to be 4 minus twice the real part of z over twice iota plus twice iota the imaginary part of z0, right? So here this is my z0, and actually I can just compute this value. So 4 minus twice, so you can actually check that the numerator and denominator, so numerator is purely real, denominator is purely imaginary. So we are going to have a phase of either plus pi by 2 or minus pi by 2, and both of these are options here. But in order to determine which it is, we actually need to check whether it's iota times some positive value or negative value. So let's see. So the real part of z0 which we have computed is going to be 2 minus square root 5 by 2, and in the denominator we have the imaginary part over here, which is going to be minus 1 plus square root of 5 over 2. Okay, and so this I can check. So 4 minus 4, this gets cancelled, and overall in numerator I have twice of square root 5 by 2, and in the denominator this 2 iota and minus 2 iota will get cancelled, and I have 2 iota times square root of 5 by 2. So overall it's going to be like 1 over iota, which is minus iota, right? So the phase is going to be minus pi by 2, because with respect to positive x-axis, this point minus iota makes an angle of pi by 2 clockwise, and we know that clockwise angles are negative. So here we select the answer minus pi over 2, which is the correct answer here. Okay, so let's move to the next problem. So I hope actually you got the idea. Okay, so if not, just think about it again, maybe rewatch that same section of video and also try to solve it yourself. So let's see the next problem. This also appeared in JEE Advanced 2019 in paper 1. So here we are given that omega is a cube root of unity. So cube root of unity, we know that it can be expressed as e to the power iota 2 pi by 3. And then we need to minimize over the set of values mod of a plus b omega plus c omega square mod squared, where a, b, c are distinct non-zero integers. So like if I would have just wanted to choose all of them to be 0, then I could have made the expression 0 also, right? But that I can't do. So let's see what it is. So first thing what we can try to do is that let's try to expand out this expression, and we can use here the identity for mod of z1 plus z2 plus z3 squared. So this is going to be mod of a square plus mod of b square, b omega square plus mod of c omega square squared plus twice the real part of a conjugate b omega plus twice the real part of b omega conjugate c omega square plus twice the real part of a conjugate c omega square. Now ABCs, all of them are integers, so their conjugate is also going to be the respective values ABC. And you can also now use this identity that real part, suppose if alpha is real, then real part of alpha times z. Okay, so z in general can be complex, so this is going to be alpha times the real part of z. So this identity we'll have to use. And also we can check that mod of a square b square c square is just going to be a square plus b square plus c square, right? So this is going to be plus b square times mod of omega square, and mod of omega square is 1, plus c square times mod of omega 4, which is also going to be 1, right? Plus twice ab times real part of omega plus twice bc times real part of omega conjugate omega square, right? And omega conjugate is going to be 1 over omega, right? Because omega is of unit magnitude, so omega conjugate is going to be mod omega square over omega, right? Which is 1 over omega. So this is going to be 1 over omega. Then I have plus twice Ca, the real part of omega square. So overall I am going to get a square plus b square plus c square plus 2ab. So now let's see what is the real part of omega. So this, if we expand out, is going to be cos of 2 pi by 3 plus iota sine 2 pi by 3. Right? So it lies somewhere here. And you know that cos of this value, if you compute, it's going to be minus half plus iota times root 3 by 2. So the real part of omega is going to be minus a half plus 2 bc times again real part of omega, which is minus a half, plus 2 ca times real part of omega square. Now omega square is going to be e to the power iota 4 pi by 3, okay, and which is equal to actually omega conjugate itself, because so here I have this point 2 pi by 3 and here I have this point which is 4 pi by 3. Okay, so there's 2 pi by 3, 2 pi by 3, 2 pi by 3. So actually omega square is also omega conjugate, because actually we saw that omega square is going to be 1 over omega because omega cube is 1, and we have seen that 1 over omega equals omega conjugate. So real part of omega is same as real part of omega square, which is minus a half. Okay, so overall now I have this expression a square plus b square plus c square minus ab minus bc minus ca. This I can write it as half of a minus b squared plus b minus c squared plus c minus a squared. So just check and verify that this is true, because you are going to get a square and a square terms twice. So multiplied by half, that will give me a square. Similarly, I get b square and b square twice. Multiplied by half, that will give me b square, and similarly for c square. And then I have these terms for minus 2ab by 2, which is minus ab, minus 2bc by 2, which is minus bc, and minus 2ca by 2, which is minus ca. So here you can check that all these terms are going to be positive. And if I have to minimize this expression over positive integers or over non-zero and distinct integers, then it makes sense to choose these integers to be consecutive values, right? So I can suppose if I choose them to be 1, 2 and 3, which are consecutive values, then this is my a minus b, b minus c, and then a minus c. So I have to minimize this expression, which is sum of squares. So it's best to make them as small as possible, which comes up only if they are consecutive. And this value will turn out to be half of 1 square plus 1 square plus 2 square. So you can check, this is 6 by 2, which is 3. So the final answer is going to be 3. So this is an integer type question, and this is your correct answer. Right, so this was relatively easy as compared to the previous question we saw. So now let's look at another problem. This is now from JEE Advanced 2018. This is from paper 1. So here, as before, z is going to be a complex number, then arc z is denoting the principal value, and principal value lies in the interval minus pi to pi, open at minus pi, closed at pi. Then which of the following are false? So note that we have to select the false statements, right, not the true ones. So here it says argument of minus 1 minus iota is pi over 4. So minus 1 minus iota is going to lie somewhere here, right? And the argument is going to be how much? So this is going to be minus 3 pi by 4, right? It's in clockwise orientation with respect to positive axis, so it's definitely not pi by 4. So this is false, so we'll select this. Next it says the function f from reals to minus pi to pi given by f of t is argument of minus 1 plus iota t. This is a continuous function. Okay. So let us see how does this function look like. So f goes from r to minus pi to plus pi, and how is this function defined? So basically I need to look for the argument of minus 1 plus iota t. Okay. Suppose if I have some value t over here, then I'm going to compute this argument, which is minus 1 plus iota t. Okay, so this argument will change with respect to t. So suppose if t goes, so let's look at t and f of t. Let's try to plot this. So when t is almost infinity, okay, so it's as large as possible, this argument of theta of t is going to be plus pi by 2, right? So from at t equals infinity, it starts somewhere close to plus pi by 2, and then as t decreases, as t becomes 0, then I have minus 1 and it reaches the value pi. Okay, so actually earlier it's slightly larger than pi over 2 because we are slightly less than infinity, and this angle keeps on increasing till it becomes pi. At t equals to 0, it is pi, but after that, as we move the curve below t equals 0, so here I am going to have when t is less than 0, I have minus 1 plus iota t for t is slightly lesser than 0, and this angle is now slightly lesser than minus of pi. Right? So here later it starts from minus of pi, and then we know that this angle keeps on increasing and finally it becomes minus of pi by 2. As t becomes minus infinity, it will go to minus of pi by 2. Right? So you can check that. So for those of you are in class 11, so since you have complex numbers, so you might be watching this video, right? But you will study continuity formally in class 12, and so continuous function is the one wherein, like, intuitively you can think of it as a function which you can draw without lifting your pen. Okay, so there is no such sort of so the function, the plot never breaks at any point. For those of you who are in class 12, you already know the formal definition. You know that it's the one where the limit exists and the value of limit equals the value of the function at that point. So here we see that actually, if you see, so here there is a break in the plot. Okay, so there is no continuous plot, and you can also check that the limit at t equals 0 does not exist. Why? Because left hand limit is minus pi, right hand limit is plus pi. So the limit itself does not exist. The value of the function at t equals 0 is pi. So here what we have is that limit of t approaches 0 from left, f of t is going to be minus pi, whereas limit of t approaching 0 from right, f of t is going to be plus of pi. So this right hand limit actually equals the value of the function, but left hand limit is different from right hand limit. So actually limit does not exist here, and of course it is discontinuous. So it's discontinuous at t equals 0, which means that this statement is false. So we'll select this statement. Next, we have the next statement that we are given the complex number z1 and z2. Then arc of z1 by z2 minus arc z1 plus arc z2. Is this an integer multiple of 2 pi? So if I compute the value of arc of z1 by z2, okay, then you can actually check that it is indeed arc z1 minus arc z2 up to plus minus 2 pi. The reason being that, suppose if z1 equals r1 e to the power iota theta 1, z2 equals r2 e to the power iota theta 2, then z1 by z2 is going to be r1 by r2 times e to the power iota theta 1 minus theta 2. Right? So basically, the argument is going to be theta 1 minus theta 2, but you may have to add or subtract 2 pi in order to bring it in the range of minus pi to pi, because if we know that theta lies between minus pi to pi, theta 1 and theta 2 both lie between minus pi to pi, but the difference may lie somewhere between minus 2 pi to minus pi also, or minus pi to pi, or pi to 2 pi also. So basically it may lie outside the range, and we may have to add or subtract 2 pi to bring it inside our range. So essentially arc of z1 minus arc of z1 by z2 is going to be arc z1 minus arc z2 plus minus 2 pi. So if I compute arc z1 by z2 minus arc z1 plus arc z2, I am going to get either 0 or plus minus 2 pi, which all three are multiples of 2 pi. So this is actually a true statement. So we will not select this. Now for three distinct points z1, z2, z3, what is the locus of the point arc of z1, z minus z1 by z minus z3 times z2 minus z3 by z2 minus z1 equals pi. So this statement says that it lies on a straight line. So let's check whether it's true or not. So I have, let's say, okay, so again we'll have to look at a geometric version. So we have seen that in almost all the questions there is some sort of geometric intuition which we are using. Okay, so here I have 3 points Z1, Z2, Z3. Now if you look at Z minus Z1 by Z minus Z3, so here I have a point Z, and okay, so Z minus Z1 by Z minus Z3. So here essentially this is going to be the argument of Z minus Z1 by Z minus Z3 is going to be the angle which Z minus Z1 vector is making with respect to Z minus Z3 vector. Okay, so here this angle, and then I have times Z2 minus Z3 by Z2 minus Z1. So it's the angle which this Z2 minus Z1 is making with respect to Z2 minus Z3, right? So here again we'll have okay, so here we have this angle, and what we know and what it says is that this argument, the sum of these arguments is going to be plus pi. Okay, now we know that for a cyclic quadrilateral this is indeed true, right? For a cyclic quadrilateral this does hold, that the sum of these two opposite angles, it does equal pi. And here note that for Z we have Z2 minus Z minus Z1 by Z minus Z3. Here we have Z2 minus Z3 by Z2 minus Z1, right? So it's the angle which Z minus Z3 is making with respect to Z minus Z1. So in this direction. Earlier we had this direction, and so here, like for example, for this figure, both of these they lie in a clockwise sense, right? But I could have flipped the figure, then both will lie in anti-clockwise sense, so that's also fine. But this lies on a circle for a cyclic quadrilateral, wherein all these points they lie on a circle. So if I fix Z1, Z2, Z3, and if I choose the locus of x, locus of z, then it's going to be the set of points which lies on the circumcircle corresponding to the triangle obtained by joining Z1, Z2, Z3, right? So these points actually form a triangle. I'll have a circumcircle, and Z lies on this circumcircle. So here essentially Z is going to lie on this circumcircle, so it does not lie on a straight line, right? So this is false because it lies on circle actually. And in this case the statement is false, so we'll select that. Okay, so just try to understand all these 4 statements again. Maybe pause the video, look at the problem again, try to solve it yourself. So now this is another problem from JEE Advanced 2018 now. This is slightly difficult one, but we'll see how to solve it. So here we are given that S, T and R, they are non-zero complex numbers, okay, and L is the set of solutions x plus iota y which satisfies the equations sz plus tz bar plus r equals 0. So here z bar is x minus iota y. Then which of the following statements are true? So first one says that if L has exactly one element, then mod s not equal to mod t. Second one says that if mod s equals to mod t, then it has infinitely many elements. The third one says that the number of elements in the set L intersection Z such that Z minus 1 plus iota equals 5 is at max 2. And fourth state that if L has more than one element, then it has infinitely many elements. So let's try to understand all these 4 statements. So note that between A and B, if you see, it appears that the answer should have something to do with whether mod s equals to mod t or not. So let's see. So we have to solve for sz plus tz bar plus r equals 0. So note that this is not exactly one equation but 2. Why? Because for s and t and z, of course, they are all complex numbers. So we'll get one equation for the real part, one for the imaginary part. So in order to solve this, we can either separate it into real and imaginary parts, or what I can also do is that I can take the complex conjugate of the above equation, right? So let me take the complex conjugate. So now I have 2 equations, right? And in order to solve them, and actually I have 2 variables also, sz and z bar. So I have 2 variables and 2 equations. So let's see if we can solve this equation. So suppose if I want to eliminate z bar, then I need to eliminate this t z bar term and s bar z bar term over here. So if I multiply this by s bar and this by t, that and subtract them, that will actually eliminate z bar term. And with z, the coefficients are going to be mod s square from the first one minus mod t square from the second one plus rs bar minus r bar t is going to be 0. So here I can actually solve for z as r bar t minus rs bar over mod s square minus mod t square. So this is going to be my z. Okay. But note that if mod s square equals mod t square, then I can't actually solve this, right? So here essentially if mod s is not equal to mod t, right, then I'm going to get a unique solution. Right. If mod s equals to mod t, right, then and rs bar minus r bar t is non-zero, then I'll have 0 plus something non-zero equals 0. So then there is going to be no solution. Okay. And yeah, and suppose if so in general, let's try to solve for the case where mod s equals mod t. Okay, so suppose mod s equals mod t and say rs bar equals r bar t. Okay, so let's see what happens here. So this is the only case which is remaining. So here I have sz plus tz bar plus r equals 0. So since mod s equals mod t, so I can select s equals say some k times e to the power iota theta s and t equals k times e to the power iota theta t. Okay, so they have same magnitude, which is k, which I have chosen. And now substituting this in the above equation, I'm going to get k e to the power iota theta s z plus k e to the power iota theta t z bar plus r equals 0. And now actually this equation looks quite similar to z naught plus z naught conjugate z conjugate plus some r equals 0, except that right now we don't know whether it's of exactly that form because they may not be conjugates of each other. So in order to make them conjugates, I can take out this part common, e to the power iota theta s plus theta t by 2. And now I have e to the power iota theta s minus theta t by 2 z plus e to the power iota minus of theta s minus theta t by 2, and then I have z bar plus of r equals 0. And now I can actually write it as, suppose if I write this as z naught and I write this as z naught bar, right, they are actually conjugates of each other, then it looks like z naught plus z naught z naught bar plus r times r by k times e to the power minus iota theta s, or let's say k can be 0, so let me retain the k over here. So I can actually combine k with these values and then I can call this k times e to the power iota theta s minus theta t by 2, that I can call as z naught. Okay, so this equals 0, right? So this actually now mostly looks like the equation of a straight line, except that this term is not real. And if this term is actually not purely real, then what is going to happen is that this is something real, right? Because it's the sum of two complex conjugates. And if this is not real, then there is going to be no solution. But if actually this is also real, this turns out to be also be real, then I'm going to get the equation of a straight line, right? So basically, if r times e to the power minus iota theta s plus theta t by 2, if this is going to be real, then we have an equation of straight line, right? Okay. So essentially, if this is a straight line, then we are going to have infinite solutions. So you can actually also check that this condition and rs bar equals r by t. So just verify that whether they are equivalent or not. So this is a homework I'm leaving for you. So essentially now we have obtained three cases. So suppose if mod s equals mod t, not equal to mod t, then we have unique solution. Mod s equals to mod t and r times e to the power minus iota theta s plus theta t by 2. So suppose if this is not real, then there is no solution. And if mod s equals to mod t and this is actually real, then we have straight line, which means infinite solutions. So let's look at the options now. So if L has exactly one element, then mod is not equal to mod t, right? Because so here we can either have unique solution, no solution, or infinite. So for unique solution, only this case gives us unique solution where mod is not equal to mod t. So here it says which of the following are true. So here, yes, so this is the only case where we can get exactly one solution where mod is not equal to mod t. If mod is equals to mod t, in which case it's a straight line, then it has either, okay, so if mod s equals to mod t, then it can either be straight line or no solution. If it has if it is a straight line, then it has infinitely many elements, but this is not necessarily true, right? Because no solution is also possible. So this option is not true. The number of elements in the set L intersection Z such that mod of Z minus 1 plus iota, okay, so Z minus 1 minus iota here, this is equals 5. So this is basically a point 1 minus iota and you have a circle of radius 5 around it. And it says is that number of elements in L intersection this circle. Now L can either have one point or it can have no points or it can be a straight line. A straight line can intersect a circle at 2 points, and L, if it is not a line, then L can either be a point outside or on the circle, right? Or it can have no solution. But at max we can intersect the circle at exactly at most 2 points, right? Either 2 or 1 or 0. So here this is also true. We have at max 2 points. If L has more than one element, then it has infinitely many solutions, right? Because we just have three cases, either one solution or no solution or infinite. So if it has more than one, then it has infinite. It's a straight line there. So these are all the options. So let's come to the final question which we will solve in this video. So here we are given four real numbers a, b, x and y, and we know that a minus b is 1 and y is not equal to 0, and z equals x plus iota y satisfies that imaginary part of az plus b over z plus 1 is y. Then what are the possible values of x? Okay, so this is the imaginary part of az plus b over z plus 1. Okay, so suppose if we are given that z is x plus iota y, okay, and let's see what is the imaginary part of this thing. So in order to compute the imaginary part, what we can do is that we can multiply the denominator and numerator by z plus 1 conjugate. So multiply it by z plus 1 conjugate, right? This equals y. And now basically I can take out this common mod of z plus 1 squared, and in the numerator I can take in the imaginary part of az plus b times z plus 1 conjugate. This equals y. Right. So here essentially the denominator is going to be mod of z square, which is like x square plus y square plus 1 plus twice the real part of x, which is x. And from the numerator, what are the terms I have? So I have a times mod z square plus bz conjugate plus az plus b, right? So this is a real term, purely real. This is also real, and from this I'm going to get some imaginary term. Let us see what it is. So here it's the imaginary part of, I can throw away the real parts. So a times x plus iota y plus b times x minus iota y, and again, so here these are reals, I'll throw them away. Denominator is x square plus y square plus 1 plus 2x equals y, and here now the imaginary part is going to be ay minus by. So a minus b times y over x square plus y square plus 1 plus 2x, which equals y. And a minus b we are given as 1, and we are also given that y is non-zero. So since y is non-zero, I can cancel away y from both sides, and now I get x square plus y square plus 2x plus 1 equals 1. So now I can just simplify it as x plus 1 square plus y square equals 1, which gives me that x plus 1 is plus minus square root of 1 minus y square, or x is minus 1 plus minus square root of 1 minus y square. Right. So here we have two possible values of x given a y, which is minus 1 plus square root 1 minus y square and minus 1 minus square root 1 minus y square. So these were the IITJEE Advanced problems from complex numbers. Thanks for attending the lecture. Bye. So do solve these problems yourself. Maybe now take some newer problems which are say before 5 years and try them yourself. Also try to understand the solution of these problems fully. If you have any questions, you can post them in comments. Okay, thank you.